Okay, so today, polynomial functions. Kind of a lot of review on this, but it's really important to get the basic things down as we look at the analysis of these for the next few days. Okay, so we need first off define what we mean by polynomial functions.
He was lead blocker for Walter Payton.
Okay, so first off, what are these? Well, what does the word poly mean? Poly means, what do you say? Many, right? And then
One more fact.
nomial, the nomial means just terms. So basically this is that you have many terms, and of course what we do in these, we just add or subtract those, so many terms added or subtracted. Alright, so here's my A, kind of define what we mean by that. So B, let's go through some examples. And again, you've seen these before, but it's good to know the terminology, because often we're a little sloppy with that, or we start throwing these terms out. These things can range from very simple, f of x equals 8, just a constant. They could be the linear form, 11x plus 8. Could be the quadratic form, 12x squared plus 2x plus 16. And in fact, we can get very high powers, like we have 5x to the 102nd plus 2x squared plus 16, something like that. All those are examples of polynomials. All of them have many terms, although we could have had some zeros on this, but many terms and added or subtracted together. So I guess it may be important to look at what do we not have. So what things are not polynomials? Well, we can't have any rational terms. So what do we mean by a rational term? So a rational term would be, well, we'd have a variable in the denominator. That'd be a rational term, right? And we have none of those in polynomials. Also, there are no radical terms. Square roots, cube roots, which would be the same as saying there's no rational exponents. So we don't have any terms that are 6x to the 1/5, right? Or 2x to the 1/2. Those are not in polynomials. Okay. So let's review the general form. Again, I think most of this is a review, but we'll probably go a little bit more in depth than you had last year. Okay, so the general form, often written like this, because basically each of these terms has a coefficient. So we use a of n. We're going to put little subscripts on our variables just to make them different. A simple numbering system. So n is just a number, a natural number, x to the n. And then it just keeps going a to n minus 1. Just keep counting down. X n minus 1. We count all the way down till we get to a to the first, x to the first, and then a to 0. So like an example. So if we had f of x is 2x cubed plus 5x squared minus x plus 7. Okay, so what is a to 3 equal to? A to 3 is 2, right? Because this is how we're doing things. Sometimes I know when you first do this, it looks really complicated. It really isn't. It's just the way we're numbering things. A to 3 is the coefficient in front of the cube term, right? Just like saying a to the 1 would be what? -1. Good, yeah. It's the coefficient in front of the linear term. Or we could say that a to 0 is equal to 7, right? The 0 means that's... Well, what is my exponent on this, technically speaking? We don't write the x, but we could. We could write this as times x to the 0, right? Because x to 0 is actually just 1, right? And that's why this is a to 0, x to 0 is 7. So we usually don't write that, but it could be written there, so it fits our notation. Okay, so that's how we set that up. Like I said, it really looks more complicated than it is. And then some different terms that we need to be aware of, that we talk about when we talk about polynomials. The first one is the degree of the polynomial. So how is the degree determined? You had this before. What's the degree? What's the degree of my example here? This would be degree 3, right? The degree is just the highest power. If you look at all the terms, the highest power. This is the highest power in the polynomial. Right, highest power. Often we talk about the leading coefficient. And that is the coefficient of the highest power. So if we look at my example here, what's the leading coefficient? The 2, right? The highest power is 3, so it's a coefficient of that term. So my example would be 3. Is what we have. And the other one that comes up is the constant term. And of course, that's we could define this as a coefficient of the term x is 0, right? Which we usually don't write that on it, but it's that term. So in my example, what's the constant term?
7.
It would be 7, right? There's something to be 7. Okay, so let's review some of the basic graphs of these polynomials. as we analyze polynomial functions, the graphs are a big help. And you already know the graphs of degree 3 and below. So let's review those. So in other words, if we had a degree 0 polynomial, so example could be, right, f of x is 2x to 0, which would be the same as f of x equals 2. What would that graph look like? What's the graph of fx equals 2? Same as y equals 2, right? Would be what? Just a straight line. A straight line at 2. Okay, so that's a degree 0. If we move up to a degree 1, well, see, and you spend a lot of time in Algebra 1 looking at these, that would be like f of x is 2x plus 3. So we know what that graph looks like, right? Straight line, y-intercept of 3, slope of 2. In Algebra 2, you spend a lot of time on degree 2 polynomials, also known as quadratics. We just talked about vertex form, graphing these out right. This one would simply be at 2, 3 is the vertex. Like that. And we talked some about, we introduced you to degree 3, although not a lot of details yet on this one. But of course the basic graph is just x cubed, and we know that. Now, degree 2, 1, and 0 we can do a lot with. They're very easy to analyze. We can always get a very complete picture easily. Degree 3 on up, it becomes much more difficult. You have to do a lot more analysis to do that. Okay, so let's look at one of the key things. I think that second hour, so you guys did this last year, but let's talk about the end behavior polynomials. Okay, so as we analyze polynomials, we really look at two different parts of them on the graph. I guess I should add this is the graph of a polynomial. So we have all the stuff that happens here in the middle, and that's really important stuff and very interesting, but we're going to call that the middle behavior. Mainly that it will be the zeros. And then out here we have what happens beyond that. And this is the end behavior. But the thing about this is there's only so many options that can happen. There's just only so many options we can do, and so that way it's very predictable or easy to do. And to analyze that, we'll use what's called the leading coefficient test, which is a very simple test to do to give us that end behavior. The leading coefficient test. So the purpose of this test is simply to determine the end behavior. And to conduct the test, all we have to do is look at the degree of the polynomial and the leading coefficient. Okay, so two things you look at. Really, two things can happen. So, the first case is if we have an odd degree polynomial. So if we have an odd degree and the leading coefficient, which is a of n, is positive. And I always remember these just based on the very basic graphs. Like in this case, it's an odd degree like x cubed. That's an odd degree. Or in fact, I could base it on y equals x, or f of x equals x, the identity function. That's an odd degree.
Polynomials are always odd.
What?
Polynomials are always odd.
No, on an odd degree, it's positive. Just like y equals x, the right side goes up, but the left side goes down. Okay, and that's right. And again, think of y equals x or y equals x cubed. If it is a of n is negative, then right, it just reflects it across the y-axis, so it's up on the left and down the right. Again, we don't care about the middle, just like the outside the end behavior. And then if we have an even degree, now this is the one that Marcel you're thinking of, I think, an even degree. So for an even degree, then if you have a positive coefficient, now both sides are up. And again, it's just like y equals x squared in the simplest case. Or both sides are down if the leading coefficient is negative. Okay, let's go through a couple examples yet on this. And probably for the most part, have you draw this in behavior. Bless you. So first one I have f of x is, let's do 3x to the 7th, 2x to the 5th, 5x cubed plus 6x squared minus 20. So we have this big polynomial, but really the only thing that matters is what on this? You have this leading term. The rest of this really doesn't matter on the end behavior. The end behavior is dictated by this leading term. So I look at two things, right? I looked at it is odd and it is positive. So it's odd and positive, what's it going to look like? Right side is up, left side down. That's it. That's my end behavior. Do one more. That's pretty simple. Make sure you memorize this. Having a way to remember it. F of x is 1 minus x to the 6th. One minus x to the 6th. You ask yourself, is it even or odd?
Even.
Now these terms are out of order, but this is the leading coefficient. Leading term, I mean. So the 6 would make it even. And it is positive or negative? Negative. So what's my end behavior look like? Both are down. Yes. Again, I remember that. Oops, you can't see it. Remember that being like a, if this is a quadratic, right? If I have a negative x squared, they're both down. This is the same thing. Any negative even power is both down.